Okay, welcome everyone to today's INQA seminar for the 17th of June 2025. It's my great pleasure to introduce to you today Kartiek Agarwal from Argonne National Laboratory in the USA. And Kartiek will be talking to us about preparing ground states of critical models using spatiotemporal quenches.
Right. Yeah. Thanks, Paul, very much for the invitation. So I'm pretty excited to speak about this sort of series of works that I've been involved in thinking about how one can prepare ground states of interesting critical models using space and time dependent quenches. So yeah, so this series of works started out quite a while ago with these three works. Initially, when we were thinking about very idealized systems, idealized low energy effective field theories, and how we can use non-adiabatic quenches to generate ground states. And then more recently, the effort was really picked up by my former student McGill, Simone Bernier, who basically started asking how we can study this in realistic spin systems using DMRG. And so we've been able to discuss preparation of these ground states in critical transverse field Ising models in 1 and 2 dimension thus far. So I'm going to give sort of a more broader overview of this whole sort of line of thinking. So hopefully this is self-contained. So the motivation generally comes from the fact that we have these artificial quantum simulators, and besides the lofty goals of trying to solve some very complicated problems, there's also the goal of just trying to simulate in more idealized settings Hamiltonians that we know and love from various condensed matter systems. And one challenge there is always, well, how do we prepare ground states or low temperature states of these Hamiltonians? So generically, what we're able to do very easily is to prepare something that is a product state, very low entanglement structure. And then, and this could be potentially the ground state of some gapped Hamiltonian. And then, slowly evolve that system to change the Hamiltonian from the initial gapped Hamiltonian to, say, some interesting, maybe critical model, which has the ground state is much more entangled. And so the adiabatic theorem then tells us that, if you want to do this, you can remain in the ground state, instantaneous ground state, as long as the gap remains sort of finite, or you maintain adiabaticity by making sure that the rate of change of the gap is always smaller than the gap squared. Now, as soon as you have gap closings, this is obviously a challenge. And in particular, if you want to try to end up in the ground state of a system where the gap actually vanishes in the thermodynamic limit, so goes as 1 over L to some power, generically, the time scale that you would need to do this adiabatically will also increase, as some power of the system size. And so that's obviously something that's going to take a very long time if you have a realistically large system. So we need ways of figuring out how to do things faster. So the adiabatic approach is slow, and as a consequence, people have come up with a variety of non-adiabatic protocols. So there are these bang-bang protocols, there's counter-diabatic driving, the QAOA protocol. I'm just mentioning here these protocols without going into any detail, but they have their own strengths and weaknesses and intuition behind them. In this particular, talk, we're focused essentially here on studying certain kinds of Hamiltonians, certain critical Hamiltonians whose ground states that we want to prepare. And oftentimes, these critical Hamiltonians, they have interesting emergent symmetries. So in this particular talk, we'll be focusing on relativistic or Lorentz symmetry. And then the maxim, if you will, is that we shouldn't really be afraid of creating excitations, as in the adiabatic approach. We can create excitations, but as long as we're able to sort of shepherd them wisely, so that you end up with a bulk of your system is sort of cold at low temperature. Maybe there's some part of your system that's hot, but as long as you're able to shepherd these excitations, that's also fine, and you can do things then faster than adiabatic. And so you may ask, well, why relativistic models? Well, if you consider, for instance, a whole class of quantum systems in 1+1 dimension, these systems of interacting fermions, bosons, spin chains, if it's gapless, it's more often than not described by a Luttinger liquid theory, which in particular is, has a larger conformal symmetry, which includes relativistic symmetry. So a lot of the interesting physics in these low-dimensional models, one-dimensional models, described by Luttinger liquid theory includes this relativistic symmetry. Another type of effective field theory for these low energy states could be free fermions, free relativistic fermions, that, for instance, happens in the critical point of the transverse field Ising model. And that also, of course, includes relativistic symmetry. But even in higher dimensions, at criticality, typically there is an enhancement of symmetry. You get scale invariance, but you often also get Lorentz invariance, for instance. If a number of magnetic transitions are generically accompanied by this Lorentz symmetry. So there's a number of interesting models that we may want to explore in artificial quantum matter that have this enhanced Lorentz symmetry. And of course, I should be clear that when I talk about Lorentz symmetry, I should the speed of light here is really the speed of excitations in the model, has nothing to do with the real speed of light. But I'm going to be using this interchangeably. Okay, so what is the basic idea here? So the basic idea is this, that we can do this shepherding of excitations in these relativistic models using superluminal quenches. So what do I really mean by superluminal quenches? Well, so look at this, if you look at this figure on the right, this is the sort of local gap in the system. So on the right-hand side, you have this gap model whose ground state you were able to prepare at the beginning. On the left-hand side, you've sort of taken away the gapping perturbation, and now you have a locally gapless system. And this domain wall is essentially being moved at a speed that is v sub s, that is larger than the speed of excitations in your system, c. Okay. So you can also look at this in sort of a space-time diagram. So where you have t on the y-axis here, and so here x equals to v sub s t is this quench front, and everything below it is in the space-time region is described by massive field theory. Everything above is described by a massless theory. And sort of the very simple model that we studied initially to sort of describe this situation is just that of a Gaussian scalar field theory, which has built-in relativistic invariance, plus there is a mass term, which we control in both space and time as such, so according to the picture. Okay. So now let's ask first, what would happen if we just quenched the mass everywhere uniformly in space? We took away the gapping perturbation. If we did that, then, well, generically, if you have these excitations that travel either left or right at the speed of c, speed of light, and they're going to carry an energy which is proportional to the mass that you just quenched. And so in this case, you just have sort of a system where the energy density equilibrates to something of the order of the mass you just quenched. But now let's ask what happens when you do this quench not uniformly in space, but along in this space and time dependent fashion. So as it turns out, you can analyze this quench in a Lorentz boosted frame, which is boosted at a speed u sub s, which is c squared over v sub s. So this u sub s is actually less than c, provided v sub s is greater than c. And so it's a legitimate Lorentz boost. And so if you go into this boosted frame, you actually recover the same situation as on the previous slide. That is, the quench actually occurs at a fixed instant of time in the boosted time coordinate t prime. So it occurs at, say, t prime equals to 0. And so now you can apply, the standard intuition that we had before, where in this boosted frame, you generate left and right moving excitations that carry an energy of the order of the mass, and this is uniform. But of course, as soon as you go back to the laboratory frame, these right and left moving waves are going to be Doppler shifted. And in particular, waves that are moving along the quench front are going to be Doppler shifted by this Doppler factor eta up. And the waves going left are going, or against the quench front, are going to be Doppler shifted to the IR. So now they're going to carry an energy of the order of m over eta, whereas the right movers are carrying energy m times eta. And if you look at this region of space-time, to the left of this dotted yellow line, which is x equals to c times t, then you can see very clearly that only the cooled left movers are actually penetrating this region of space-time. And so as a result, in this region of space-time, you can expect the system to be colder, whereas on the right of x equals to ct, you can expect it to be warmer. And in particular, in the limit that v sub s goes to c, this Doppler factor is going to diverge. And so these colder waves are actually going to carry no energy whatsoever. So in fact, you're going to get something that's very, very close to the ground state in the sort of sub system. So that's basically the idea. And we can demonstrate this very easily. This is a Gaussian theory, so we can numerically investigate this very easily. So here's an example where we do this quench in a Gaussian scalar field theory in one dimension with the quench velocity v sub s being twice c. And you see exactly as we discussed in the intuitive picture that there is a region on the left-hand side, x less than c times t, where you get a cold system, and on the right, the system is hotter. And as you decrease this velocity towards speed of light c, you see that actually this Doppler shift discrepancy between the left and right movers becomes larger. So the cold region actually gets colder and wider, and the hot region becomes hotter, and it shrinks in space. So in particular, in the limit v sub s going to c, this kind of becomes almost like all the energy is carried by sort of a shock wave that keeps piling on top of itself as it propagates ahead to the right. So that's basically just a 1 + 1D situation. What happens, can this be extended to higher dimensions? So we looked at this for bosons and free fermions. So for bosons, now if you imagine there's a quench front that is moving, that's uniform, let's say in the y-axis, and then moving to the right at, again, the velocity v sub s, now in principle, this quench front generates a bunch of excitations that travel in all directions. But as it turns out that in the limit, and this was surprising to me at first, if you take the limit of v sub s going to c, it turns out that only a tiny sliver of waves that are traveling right along against the quench front, those are the ones that get heated. Almost every other excitation is Doppler shifted down. So in fact, we can see that the cooling effect is there even in this setting. So you can look at the energy density in this higher dimensional case as a function of distance, and you see that there's a hot region to the right and a cold region to the left, again, the cold region becomes colder as V sub s approaches C, hot region becomes hotter, except that now there isn't as sharp a transition as we saw in 1D, but it's a smooth sort of a curve for the energy density. Likewise, we can do this calculation for free relativistic fermions. And so here what happens, initially you have these left and right moving modes that are coupled by a mass term. You remove the mass term, then you have these left movers and right movers that are completely decoupled. And you can ask, what is their excitation spectrum? What do the populations of these modes look like? And it turns out that, compared to the equilibrium, the zero temperature case, there is sort of a hole that is punched into the occupation, but the size of this hole is essentially Doppler shifted in momentum space. So it goes as m over eta for left movers, where essentially it becomes exactly the zero temperature state in the limit of eta diverging. And it becomes, all the energy again is carried by the right moving waves. So the same kind of idea applies with some modifications to exactly how the energy density scales as a function of the velocity and so on. And this whole thing, achieves a speed up over the simple adiabatic quench, because now you can actually, as you do this quench front, you instantaneously generate sort of a very low energy system as you propagate this quench front. Of course, for the quench front to move through the entire system, that's going to take some time order L, and that's basically the time it takes for this quench to give you the ground state or something very close to the ground state. So that's basically what we had in the first version of this. And at some point, we sort of realized that, it might be a little bit tricky to extend this to actually a true or real models. So there's a number of things that, happen when you have a real, spin system, which has some lattice and there are UV cutoffs. So first of all, the UV modes, I mean, the sort of relativistic theory is for the lowest energy modes. And so the UV modes in general are not going to have this relativistic property. They're not going to have the linear dispersion. And so in general, this is actually not such a big deal, because the way to solve this is to simply make sure that if the mass is being quenched, as we were studying in the previous slides, that the mass is quenched instantaneously at a given point, in this sort of theta function form. Instead, now it is quenched at a time scale tau, where as long as tau is of the order of the UV cutoff inverse, you can make sure that the UV modes are, just by standard adiabaticity, they're never excited. And so all the excitations are of the low energy modes, which can then be this cooled using this Lorentz cooling effect. So that's one thing. The other thing that actually disturbed us a little bit more was the fact that if you add up the energy, so you get the separation of cold and hot regions. But if you look at the total energy carried by the cold and hot regions, add them up together, as it turns out that total energy created in this process is actually independent of the quench speed. And so V sub s. So that would suggest that if your critical theory, low energy theory, is not a theory of free bosons or free fermions, you can get scattering between left and right movers, and that will generically sort of spoil this cooling effect, because now energy can be exchanged between right and left movers, and the cooling effect might be spoiled. So that really concerned us, and led us to actually come up with a very different class of quenches, which we called conformal or hyperbolic quenches, and actually shows that even if you have a very interacting theory in 1+1D at least, you can show that there will be cooling, and the cooling is a purely geometric effect. So just to explain that a little bit. So what we have here is a quench now, where the quench front doesn't occur along this superluminal trajectory x equals to v sub st, but rather is defined by this hyperbola t squared minus x squared equals to t naught squared. And so we can again play, if your theory has a larger conformal symmetry, we can again play the same trick and analyze this problem in a new set of coordinates, now conformal coordinates, psi and eta, where actually, as it turns out, in the conformal time, this quench occurs at a fixed time, eta equals to 0, and uniformly in conformal space coordinate psi. And now we can apply the same tricks of analyzing this problem. So using the symmetries of the quench and the underlying theory, we can actually, and I guess we can the fact that the quench is uniform in psi, the stress energy tensor of the CFT can only depend on eta, and it has to have a symmetric traceless form. Additionally, off-diagonal elements, which are sort of describe the currents, these can also be shown to be 0 if you have parity symmetry. So inversion about the x equals to 0 axis. And so finally, you just put in energy momentum conservation, and that actually completely determines the form of the stress energy tensor, barring a constant in front. So if you look at the top left part of the stress energy tensor, you can see that for large times, this component, which describes the energy density, will go down as 1 over t squared. And here we've made no assumptions of whether the theory is strongly interacting, weakly interacting. It just falls out from just the symmetry arguments. So that gave us confidence that some of the ideas that we're actually proposing are much more general. I should also mention, I guess, here that the limit of t naught going to 0 of this particular hyperbolic quench trajectory is precisely the superluminal quench with v sub s equals to t, just a symmetric version of it. So really, these are also related in this sense. And just a brief argument of how this works, why this cooling is purely geometric effect. Well, you're creating these excitations uniformly in these conformal space coordinate psi. So if you have something that has a wavelength d psi, when you look at it back in the laboratory frame, actually that whole space d psi is expanding. And so the wavelength of this excitation is expanding and increasing linearly in time. And of course, the region of space that it's occupying is also increasing linearly in time. So the energy density, just because of that, goes as 1 over t squared. So really, it's just a purely geometric argument that leads to cooling in the setting. Okay, so that's so far where we had, with the with all these ideas from conformal symmetry and from our studies of scalar field theories and relativistic fermions. These are all specialized models, but how does this actually work in a realistic spin system that could be realized in some artificial quantum simulator setup? So that's where Simone really worked out essentially how to make these simulations happen in DMRG, and this is not particularly simple because these are so let me just say the model that we are going to be studying is, at least in one dimension, this is the transverse field Ising model, but with long range interactions. And we considered this, again, motivated by experiments because if you have, for instance, a Rydberg atom setup and you have van der Waals interactions between the Rydberg states, you're going to get generically a 1 over r to the 6 interaction. If these have dipoles, dipole moments, then the interaction will go as 1 over r cubed. And if you look at ion traps, which is another candidate for simulating these spin models very naturally, then the interaction is even more long range with something like 1 over r to 1 over r cubed realized, depending on how the vibrational modes are configured. And so you can get a sort of a large class of different transverse realizing models where you have a transition, a critical point between, again, a paramagnet and a ferromagnet. But of course, the low energy theory can be different and is certainly more complicated than just transverse realizing model with nearest neighbor interactions, which of course is just integrable. So this model has been studied in equilibrium by Maghrebi and others, and there are G-analysis suggests that for at least for alpha greater than equal to 3, so interactions that decay at least as fast as 1 over r cubed, the critical theory is actually just free fermions, exactly like the short-range transverse realizing model, with a finite speed of excitation c and a light cone that is, the usual light cone. For alpha less than 2, actually the light cone becomes exponential. So r scales as, the region of space-time you're affecting blows up exponentially in time. And so the model is basically at that point close to being zero-dimensional. And you get more general power laws for alpha between 2 and 3. So with this in mind, we considered 3 cases, alpha equals to 6, alpha equals to 3, and alpha equals to 2, to ask, what kinds of, how does this how do these spatio-temporal quenches work in these models that can be realized in these experimental setups? Okay, so this is an example of how this looks like for alpha equals to 6, which is basically in the short range, really short range regime. So this is the color here indicates the energy density, the excitations. And the red line and this blue line, this essentially indicates the quench front, which propagates at some velocity v sub s. And what you can see is you can see this line x equals to c times t emerge. So like we had in the theory version of this, there's a region of space which is cold, this dark blue region, and then a region of space which is warmer, which is light blue. And then, of course, there's the quench front. And you can see these regions essentially expanding with the speed of light, hitting the walls and coming back. So it's really, this is the really non-integrable model, but it really exhibits the same features that we sort of expected from a non-interacting, Gaussian scalar field theory simulation. If you look at the spin-spin correlators, right, that also, let's focus on this v sub s equals to 3 case, which corresponds to the figure on top. Here you can see that the correlator starting from, sigma x correlator, starting from the middle of the chain outwards, it decays with some length scale in the cold region. And as you transition to the hot region, it decays on another faster length or smaller length scale. And in particular, as you decrease the velocity down to c, you start developing really long range correlations. And you can also probe the underlying critical exponents in the system by doing scaling collapses. So this is, here we sort of used our just free fermion prediction, which is relevant for the transverse field Ising model. And that prediction suggests that the correlation length has to be, in this quench, has to be eta times gamma. These are both relativistic Doppler and Lorentz factors. And so, putting this this correlation function and bringing out sort of the anomalous exponent, we can see actually we get a very, very good scaling collapse when we scale, the r by this correlation length and the correlation function by this anomalous exponent. It differs, depending on what tau this time scale for this smoothing of the quench is used, but otherwise, there's almost a perfect scaling collapse, and it gives you this critical exponent, which is 1/8, which is exactly what you'd expect from the ground state of the critical transverse field Ising model. And so another sort of, thing that, we can see is the energy density as a function of the velocity of the quench. And I think here this is quite well, it's nice for one because it agrees very well with the energy density expectations, again, in terms of these, relativistic Lorentz and Doppler factors. You see that the energy density decreases as you take the quench front velocity to the speed of light in the system, as we expect. But more interestingly, at some level, you see that as you decrease the velocity further, you actually start getting heating again. And that you would not get from just simple adiabatic thinking, right? If you move the quench front velocity slower and slower, you'd expect that you produce even less excitations, which really highlights the fact that this cooling here is really down to this kind of geometric effect of the Lorentz cooling and not just, some adiabatic process. If you look at the same plot for alpha equals to 2, that's this really sufficiently long range model, this minimum is basically absent. So you see that as you decrease the velocity, you get lower and lower in the amount of excitations that you're generating. Okay, so how am I doing for time actually?
Yeah, you're kind of a bit over, but I'm not going to be strict about this, don't worry. So round up in good time.
Sounds good. So I should just say that, even though, we can't predict exactly what's going on in this alpha equals to 2 case, we can nevertheless do some kind of a scaling collapse and try to get a sense of what are the relevant energy scales, length scales in this problem. And we do so by essentially, borrowing from the standard ideas in the Kibble Zurek literature, which is that there is a typical length scale for excitations if you do a quench sufficiently fast, which scales as such. But then since this is an inhomogeneous quench, there's another length scale, which tells you if you created sort of a system with a symmetry broken state on one side, symmetry preserved state on one side, how much does the order parameter leak in to the other side? That's characterized by this psi SP here. And it's these two length scales that really have to determine, if this analysis is sensible, they have to determine essentially the scaling of the energy density. And indeed, that's, again, with the scaling collapse, we verify that that's the case. And we extract critical exponents that, are very close to what was predicted in the Maghrebi paper. Right. So just a final slide here on the simulations in the two-dimensional case. So in the two-dimensional case now, so this is transverse field Ising, 2 dimensions, nearest neighbor interactions only. This is already very, very challenging to simulate. And in this case, we sort of have even the least expectation at some level for this to work because the critical point in the 2D transverse field Ising model is actually a strongly interacting scalar field theory. So we can't really make the assumptions of like non-interacting bosons that we use to derive these ideas. Nevertheless, actually, I mean, somewhat surprisingly, I'd say you see the same kind of heat wave phenomena. You see cold regions, warm regions. This is the plot that I showed some while ago now. And you see that actually the cold regions become colder as you come closer to, as the quench front velocity approaches the speed of excitations in the system. You can also look at, say, the entanglement entropy, and the entanglement entropy, if you do the quench closer to, as you take the quench front velocity and bring it closer to the speed of excitations, you see that the entanglement entropy, half-cut entanglement entropy, approaches what you'd expect for the ground state that you get from DMRG. So that is sort of just another indicator that this is sort of working as we'd expect. Although, one thing I should say is that it's not clear if it is as effective as it was in lower dimensions. But again, I should say that this is a very, the simulation is of a quasi 2D system, and there's obviously caveats in how we interpret these results for the 2D system. So with that said, yeah, I think this is nevertheless it shows similar features essentially that we saw in 1D. Okay, so that's basically the end of my slides. Just to conclude, I discussed how we can use space and time dependent quenches to create ground states of critical models parametrically faster than adiabatic methods. We developed a very robust argument for at least one dimension that the cooling is purely geometric effect and can take place, as long as you have this conformal symmetry underlying. And the numerical simulations that were conducted by Simone sort of, with long-range transverse field Ising model and the 2D transverse field Ising model sort of confirm some of these ideas.
Great, thank you very much, Kartiek, for your presentation. Thanks on behalf of us. And I guess I'll open up the presentation for questions. Maybe I can start. Maybe this is an unfair question, but what about 3 dimensions? I mean, are you basically limited by what you can simulate in 3 dimensions? It just becomes horribly impossible, or is there a fundamental reason why you think this general technique might or might not extend to 3 dimensions?
Yeah, well, first of all, yeah, thanks for that question. I mean, we don't really have a very rigorous argument except for in the non-interacting setting. So if the critical point is described by very plain vanilla Gaussian scalar field theory in higher dimensions, then certainly this can be used. But it's not obvious how this will work for a more interacting, critical point. So that's basically the limitation on the analytical front. On the numerical front, certainly, I mean, even this 2-dimensional system, I think, was extremely challenging to study, and certainly 3 dimensions is really beyond what we could do in ultimately this is highly non-equilibrium, so somehow we need some level of accuracy and can't really rely on approximations or approximate theories for simulations. But that's basically my sense. But I mean, if they can actually demonstrate such ideas and explore underlying symmetries of the models in just 1 and 2D, I think that would be pretty fantastic. And also,
And I guess I'm slightly more familiar with the concept of what are called quantum random walks, where you essentially turn on suddenly in time a transverse field. So I guess in your language that would just be a temporal quench.
yeah.
How would you compare the 2 approaches? I mean, clearly with spatiotemporal quenches, which you've been looking at,
Yeah.
I'm having trouble sort of intuitively understanding what the differences are there. Can you help me there?
Right. So, I mean, I guess more generally, you can ask, suppose you had this lever to control the local transverse field at any point in space locally, and I mean, on each individual spin locally and in time. And so at some level, what I'm saying is that this is the best way of controlling the transverse field. Now, I'm not saying that based off of, it just seems to me that this is probably likely to be the best case scenario. But I also know that, so not precisely in this setting, but people have studied in an analogous setting, question of transport of, say, Majorana modes in topological superconductors, and applied these ideas of, say, bang-bang protocol. So that's like where you are allowed to change effectively the transverse field only between some range of values. And, it turns out you get some kind of very, large number of solutions that look different every time you sort of optimize. And it's hard to necessarily understand what is the physical intuition behind where those solutions came from. So I think there are other, sort of protocols you could envision. But at least to me, this seems to be the most physically intuitive of the lot. I don't know if that answers your question, but that's...
Yeah, kinda. Yeah, sure. I'm a humble experimentalist, so good. Well, if there are no further questions, thank you once again, Kartiek, for a very nice presentation. And I look forward to seeing as many people as possible at next week's seminar and the week after that, which will be the final of the online INQA seminars, which we're looking forward to.
Right.
Once again,
Thanks.
bye-bye.
Thanks. Well, take care. Thanks, man.
Yes, bye-bye.